Good morning. Continuing our study of space. Move on to the vector valued function. It's a function of the form f of t, g of t, h of t. F, g, and h are all component functions, and they are real valued functions of the parameter t. Where do we think this vector would be defined?
At any point given where all three elements come from the same T value.
All three elements, you mean the component functions?
Yeah.
And what do you mean come from the same t value?
If they all have the same input, then they'll work.
Well, I agree they'd have to all have the same input. Right, R of 5 would have to be f of 5, g of 5, h of 5. But when would that be defined? Right, meaning, when would it exist? As an example, 1 over 0 is undefined, right? So when would a vector be defined? So what would happen if all of f, g, and h were undefined?
R would be
Clearly R would be undefined. What if f and g are defined but h is undefined?
you get a plane.
Would it be undefined?
Be undefined, wouldn't it? You have an undefined component. So the overall vector would be undefined, wouldn't it? Which means the domain of R has to be the intersection of the domains of the components. Right? All three components must be defined in order for your vector to be defined. Oh, well, remember finding domains in pre-calculus, so this is nothing new. Do you recall the definition of the limit from Calc 1?
In order for function to have a limit, I think it must be continuous and FSC must be different function.
That's for continuity. All right, continuity, obviously, has to be defined. Function has to be defined at the point. Limit has to exist, and the limit has to equal the evaluation. But what is the actual definition of a limit?
Just describe the function's values. It's approaching a certain number.
That's true, right? That is the intuitive notion of a limit, which is what you studied first in Calc 1. But you should have also then moved on to the actual definition, right? So what you just said mathematically, does the notion of an epsilon delta definition sound familiar? Because that's what a limit definition is. It's an epsilon delta definition.
Is it the rate of change?
Oh, good. I probably could have. Gone with more lines. So let's fix that. Try to go out to 6. No, 5.5. That'll probably be better. Oh, maybe not. Oh, right, I have to shrink this. Yeah, that looks good. There's your formal definition of a limit. From Calc 1. Oh, limits are so fun to work with using that definition. Right, again, that is exactly what you said, just in mathematical terms. Yes.
I was gonna ask you.
Right, so all that's saying is you can make f of x sufficiently close to L, or arbitrarily close to L by making x sufficiently close to A. That's what that says. Well, that's for a function. Vector valued function. R approaches the limit L as t approaches A, written that way, provided the limit as t approaches A of the magnitude R of t minus L equals 0. And oh, I need to correct those because those L should be bolded. At which point you then go back to that definition. Right. Although in this case now L is 0 and f of x is that magnitude.
Wait, is L a vector?
Yes. Oops. Don't want to be there just yet. I need to. Well, that is kind of an inconvenient definition. Because just like with this definition, that's great to understand what a limit is. It's like, this is great to understand what a limit of a vector is. What it doesn't tell us is how to find that L. You should remember you had, in Calc 1, you started by looking at two techniques that gave you approximations, numerical and graphical. Right? You either form a table of values or you just look at the graph. But that's not really accurate, and it will only ever give you an estimate at best. Then you moved on to algebraic methods. Right? Method of substitution being the best one. Which runs in the problems of then your indeterminate forms, right? 0 to 0, infinity over infinity, infinity minus infinity. My personal favorite, 0 to the 0. You also have 0 to the infinity. I think 1 to the infinity is also indeterminate. And then you had to do algebra, squeeze theorem, or L'Hopital's rule. But we also have techniques to find limits of vector functions. With some considerable effort, I don't even think I did it in the video, you can prove this result. That the limit of the vector valued function is the vector of the limits of each component. If even one of those limits does not exist, then your overall limit does not exist. But wait, F, G, and H, what are they? More specifically, what kind of function?
Position.
Which is what you studied in Calc 1. So each of those three functions are just a Calc 1 function. Which means all of your techniques from Calc 1 for finding limits apply. You just have to do it 2, 3, 4, however many components you have. Oh, so look at that. We're back to Calc 1. Hope you remember your limits from Calc 1. Hope you remember all your rules. I guarantee you don't. Bet you forgot the one that's barely ever used. Squeeze theorem. Oh, just all wince. I guess you have bad memories of squeeze theorem. Or the sandwich theorem, as one of my texts call it. I refuse to call it that because then I want a sandwich. So I'll continue to call it the squeeze theorem. Well, what about continuity of a vector valued function? So when do you think a vector valued function would be continuous at a point? So we'll go here. So you would agree that it would have to, for R to be continuous, R of A to be continuous, each of the three functions would have to be continuous, right? So F would have to be continuous at A, G would have to be continuous at A, and H would have to be continuous at A. What were the three conditions? What was the first condition?
Has to be defined.
Huh?
Does it have to be defined?
Where?
At A.
Right, R of A has to exist, which means F of A, G of A, H of A all have to exist. What was the second condition?
Limit as it's approaching A has to be.
For each of the three, right? Which means for R, that limit would have to exist. And what was the final condition? Oh, well, spoiler alert.
The limit equals R at
Right? Conditions 1 and 2 have to be equal. So we are now into the fourth week of Calculus 3, and we've only done, what, one new thing? Spherical coordinates. Physics. Technically, you did vectors in Calc 2. They just didn't call them vectors. Right, generally speaking, by the time you take Calc 3, you've already taken intro mechanics. And you cover just about all of vectors there.
And the linear algebra.
Yeah, linear algebra, you do vectors in linear algebra, although more abstract vectors. Yeah, we're actually getting close to that in our linear algebra. Vector spaces. Start that soon. Yeah, don't worry, we're still not going to be covering anything new for the next week or two. find the domain, express in interval notation. All right, remember, there are two ways to express domain. Interval notation. Do you remember what the other method was from pre-calculus? We don't remember finding domains.
Is that LN11?
T is
Yes. That spacing came out really weird, didn't it? At least it looks like it did. So what was the other way of representing a domain? Interval notation and what notation? Set builder is what it's called. They are used interchangeably. But they want us specifically here to express it in interval, so that's what we'll do. Which means we first have to find the domains of the three component functions. What's the domain of the natural log of 11t?
everything except zero. Actually, everything related to it.
0 to infinity? What's the domain of the square root of t plus 10?
10 greater. Or negative 10.
Negative 10 included?
Yes.
You did say negative 10 or greater. Still haven't had enough coffee. And what about the domain of 1 over the square root of 12 minus t? No, I don't want the Copilot app. Please go away.
Greater than 12. Then 8. So 13. Or 12 parentheses. Or is it
If
opposite?
t is 13, what's 12 minus 13? That's a problem, right?
Yeah.
So negative 3 to 12, not 12.
This isn't complex analysis. So we're not allowed to have negatives in the square roots. The domain of R is then the intersection of those three domains. What is intersection? How do you find the intersection of two sets?
Just the common values.
So what's the intersection of these three sets?
And starts at 0,
Open, closed, half open?
closed, or parentheses.
That? We agree? Yeah, that's the domain. 0 to 12. All right, so remember the rules for domains.
So could you go ahead and found the intersection? So how people-
What was that?
So can you go ahead and found the intersection?
Well, he found it. So how'd you find it?
Well, if there's like a line, the range where all the values are included in each of those is the intersection. So 0 is defined for all three, and 12 is defined for all three.
I've actually never thought of it that way using lines. I like that. If you draw out the number lines, it's where they overlap. Right, where all three would overlap. I've always thought of it as Venn diagrams.
That's not what I was talking.
Of course, I generally think of more general set theory than interval, so that's probably why I default to Venn diagrams. But yeah, intersection is just what's in common. Right, where's the overlap at? I like that. I'm gonna start using number lines. So domain of 1 over x is what?
0 to infinity, not
Negative infinity to positive infinity, excluding 0.
Right, so the denominator is never allowed to be 0. That's your first rule. Remember that? Second rule. Yes, this is a fun one. Nth root of x.
Zero to infinity.
First, open or closed?
Oh.
So it's closed. And is that always true?
and
So this was a fun one.
oh, the answer did restrict that. And is even.
Right, so it's only restricted if n is even. and everything if n is odd. Now you have an even index radical, has to be non-negative. Odd index radical doesn't matter. Right, you're allowed to take the cube root of -8. It's -2. But fourth root of -32, that doesn't exist. Not in the real plane. Does in the complex plane. Domain of e to the x was what?
So that's just all the groups.
Natural log of x, we just kind of went over.
Not including 0. So
0 to infinity.
Open or closed? Domain of sine?
0 to
0 to 2.
no. So negative.
It's everything. Same as cosine. What's the domain of tangent? Let's see if you remember.
0 to 1.
Thing that doesn't equal pi or 2 or 3 pi or 2.
Just those two values?
Or any coterminal ranges of those.
Everything except odd multiples of pi over 2. Right, everywhere where cosine is 0. Which is the same as secant. All right, so tangent secant have the same domain. Do cotangent next. ever except multiples of pi. Right, so wherever sine equals 0, which is the same as cosecant. And then, of course, we have the inverses. Domain for inverse sine is the same as for the inverse cosine.
-1,
Closed or open?
closed.
-1 to 1. Domain for the inverse tangent, which is the same as the inverse cotangent. It's everything. And then inverse secant and cosecant. Again, their domains are the same. I will write this in set notation because it's easier. It's everything where the absolute value of x is greater than or equal to 1. So everything except between -1 and +1, not inclusive. Remember, the domains of the inverse trig functions are the ranges of the trig functions. The ranges of the inverse trig functions are where it's a little bit different, right? We had to restrict it, but I'm not worried about that. So those are the rules you need to remember. And you should remember those from pre-calc. If not, this is a good refresher. And it might be on one of those tables, either the basic functions or the review of pre-calculus. Now, at this point, we don't need to worry about parametric equations because we can just write it as a vector parameterization. So write the vector parameterization of a circle, radius 6 in the xy plane, centered at the origin, and then verify that this is a proper parameterization. Start with a set of parametric equations of just a circle of radius 6, centered at the origin. Well, it's not even centered at the origin. Centered at AB. I'll do even radius R. I'll just do the general parameterization. Do you remember what this is?
Six cosine 2, 6.
What was it?
X would be 6 cosine 2, and y would be 6 sine 2.
This is a very important parameterization. It should have been studied in Calc 2. Say should have been. Doesn't mean it was.
Wait, wouldn't it, but, so wouldn't the X component just be sine? Or sine?
That's your general parameterization of a circle. Right, so that may be one you want to write down and remember. If the center is the origin, then you just get R cosine theta, R sine theta, which is what you expect. So let's relate that to here. Let's move that up. X component. A plus R cosine theta. What's A? What was it? 0. Centered at the origin. What's R? That's the 6. Y component. What's B? 0. Centered at the origin. What's the Z component?
Sure.
Why?
There's no, so it's just, well, it's not in the Z. It's not going up or down in the Z. That's,
How do you know?
the circle.
So
It wouldn't have 3 dimensions.
I can draw a circle centered at 0, 0, 5 that only stretches out in an xy plane. Now there's a z component. But it's still two-dimensional.
So that's my plan.
It's on the xy plane, which is z equals 0. Like, that's why I was asking, how do you know it doesn't go up or down? Because it's in the xy plane. Right, if this is the xy plane here, here's your circle, right? Let's say there's z equals 6. Same thing, except now that 0 would be 6. But it's still two-dimensional. Because it's still on a plane. It just happens that that plane was lifted up. And whenever you do a vector parameterization, you need a domain. And in fact, that's true no matter what kind of parameterization you're doing. You need a domain. Any interval that has a length of 2 pi would suffice. Right, so negative pi to pi would also work. Pi over 2 to 5 pi over 2 would work. Right, anything along those lines. This is the standard though, 0 to 2 pi. When it comes to actual calculations, it doesn't matter if you include that 2 pi or not. Technically speaking, you don't include it because it's already included in the 0. And if you include it, you're including the same point twice, which you typically don't want to do. Oh wait, I have to verify that this is now proper parameterization. Ah, yes. The biggest curse word in math. I have a math person here, don't I? Thought I did. No math majors? Yeah, that's I knew I did, yeah. You're gonna hate this word. That was easy. That starts it. Since z equals 0, we're in the xy plane. Perfect. Now it just boils down to, does that parameterize a circle of radius 6? X squared plus y squared. All right, replace x with 6 cosine of theta, replace y with 6 sine of theta. You can factor out 36. What's sine squared plus cosine squared? X squared plus y squared equals 36. Is that what we should get? Yes. That would be the relation for a circle centered at the origin of radius 6. So the proof is complete. So I need to split this. Oh. Well, that's annoying. This is a matrix. Okay. I want one row. How does that work? Perfect. So let's start with part A, and then we'll look at the other parts separately. Vector parameterization for the line through the points 4, 1, 1 and 9, negative 3, 3 for each of the following conditions. So actually what I might do is for now, ignore any of the conditions and just look for this. Remember what we need when you parameterize a line. You need a point and a direction, don't you? What's our direction?
Q minus C.
Define what you mean by Q minus P.
The components.
Like, technically speaking, you can't subtract a point from a point. That doesn't make sense. But if you're talking about subtracting the components, then yes. Or could you do P minus Q? Does it matter?
It's going through P first.
How do you know?
The opposite direction.
Yeah. How do you know it's going through P first? Nowhere does it tell you it's going through P first. It's a line, extends forever in both directions.
Yeah. But I mean, the magnitude would be the same direction. Right.
True, but how is it different? How would the direction be different if you flip the order?
Well, you would get a different result for them.
And so let's say that's the direction. What happens if I just change the order of the points? Direction is just off by pi. Still the same direction of the line, right? Would still be parallel to the line. So the order doesn't matter. You can do PQ or QP. As long as you're consistent. 9 minus 4 is 5. -3 minus 1 is -4. 3 minus 1 is 2. Okay, that only has one negative. I'm happy with that. That's the direction I'll use. And there's unfortunately no simplification. I can't like factor scalar out. I mean, I could, but then I'm gonna have a fraction. I'd rather avoid that, if at all possible. So our line would have the parameterization 4 plus 5t, 1 minus 4t, 1 plus 2t. For all t.
Can you use and Q?
Yeah, you could have. So I'm now going to write that way. And there's a reason for that. This t here, it's just the parameter, right? So couldn't I replace that t with anything as long as it can take on all values from minus infinity to positive? So I'm going to replace it with f of t, some arbitrary function of t. Where the range of f of t is all real numbers. Right, that's the important part. Is that whatever function you decide to use has to give you all real numbers as an output. So I could use like t plus 8. Or some really funny I lost my train of thought. Really funny, like 100th degree polynomial. And it doesn't matter as long as I can get all real numbers out of it.
Wait, so why are you adding p onto that at the start, like 4 plus 5 minus?
What's the parameterization of a line? So that's what it is. X naught plus AT, Y naught plus BT, and Z naught plus CT. You could have used the point Q as well if you wanted to. right, but this is the important part here. Our line has to have that form. And now we're being asked to have it satisfy certain conditions. And this is where we'll pick up. Now we have the general form of the line. We'll start to satisfy those conditions on Thursday. Two new assignments are now available. Second discussion assignment, which I believe is on the use of generative AI in mathematics education. And the second project went up. Groups should have been assigned already. Second project, oh yeah, that's a fun one. Proving Kepler's laws. Kepler's laws of planetary motion. That's a really good one. That's a fun one. Johannes Kepler.
Discussion already up.
Yes, discussion went up this morning, midnight. Right, as with before, your initial post is due first. So in this case, the 13th. Then you start the responses, which will be due Monday. So what's the 13th? Thursday? So your initial post is due Thursday night.